Hi, Professor Hoback here with another edition of I don't really know what I'm doing, but I'm going to show you anyway. So today we're going to talk about knife geometry. In particular, folding knives. Now you say, Professor Hoback, the internet is askew with all sorts of information, most of it conflicting on how to properly design lock geometry and detent geometry and everything else that there is to know on folder design. What makes you think that you, of all people, know what you're talking about? I don't, but I'm really good at winging it. So let me erase the board and we'll get started. Alright, so you probably have, if you're trying to be a knife maker, or maybe you're just a collector trying to understand how knives work, you've probably scoured the interwebs, looking on forums, and talking to other knife makers, and everybody else, you know, everybody has an opinion on lock geometry. So again, this is an opinion. You know what the saying is, something about armpits and nether regions. So this is my opinion. This is what works for us. I've made many thousands of folding knives. I'm pretty well experienced in it. If you don't know a whole lot about me, I've been a knife maker for almost 2 decades now. Been making folding knives for over a decade, and I've gotten pretty decent at it, I guess. Most of our stuff sells, some of it doesn't. But, you know, for the most part, I've dealt with a lot of problems along the way, and I'm hoping this video in the Professor Hoback series will kind of help you delve through some of my trials and errors that I've had with lock geometry, and with any luck, make it easier for you to make a knife. Nowadays it's pretty easy to just you know, be a knife designer, draw something up with crayons and a napkin, send it off to a company, and voila, you have a knife, and now you're a knife maker. All the while not have gone through all of the trial and error to actually figure out lock geometry and everything else. So maybe this will help you. Maybe you're just a new knife maker and you're just looking to like figure out the hows and whys. There's many different ways to skin the cat. The way I do it is not set in stone. I am always looking for new, better ways to do things, more efficient ways to do things, less expensive ways to do things. Right now, the way I cut lock geometry is rather expensive, just because it requires a great deal of machine time. You can do it on the cheap. You can do curved lock faces, you can do flat lock faces, you can do angles, like steep angles, shallow angles. There's a million different ways to do it. This is what works for me. I've seen it work other ways, but I chose to go the way that I do it just because of all the experience that I've had, and my machining capability. This is the easiest way for me to do it with the least amount of hassle. You know, as a businessman, entrepreneur, I want to find the best way to make something so that it is the best quality product and the best offering that I have the ability to make. But I also have to take into consideration what is the least amount of hassle and the most cost-effective way to do it. So that's how I do it. You know, if you're just a custom knife maker or getting into making knives and you want to do this on the cheap, there are other ways you can do it. I'll try to explain some of that, but I really don't want to make this video crazy long or anything, so I'm going to try to be quick. I'll try to answer your comments and stuff. I'm pretty busy, dude. This is like one of the rare times in the shop that it's quiet enough that I can do video work and get away with it. I'm sure we'll have people opening up the doors here shortly. I got in before everybody else, but hopefully you can pardon the interruptions if we have any. And let's go on. So, folding knife geometry. First thing we're going to do is talk about the lock. Everybody wants to know the lock. So there's a couple things you have to keep in mind. I'm not going to be able to, in a short 10 or 15 minute video, give you every single little detail on this. Some of this you're just going to have to trial and error because it's good for you. Builds character. I know I have lots of character because of it. So what you want to take into consideration when you're designing a lock is the length of the lock bar. So I'm going to abbreviate some of this stuff, so I'm going to have to spell it all out. So length of lock bar. Okay, so I like that. LOL. So then you have to take into account angle of lock face. I like acronyms. And then you have to take in to curve or not to curve your lock face. Okay. So, if you're totally green to this, you have no idea what I'm talking about. So, let's start with the length of lock bar, LOL. So, you have your blade. Okay, these are going to be really crude drawings, so forgive me. Here's your blade. Here's your pivot hole. Here's the front of your handle. It's awesome. I should just make this. It's perfect. So, your length of lock bar. Your length of lock bar is going to be, hopefully, as close to and below the center line of the pivot as possible. Okay, you do that because there's a multitude of different ways. Just trust me, do this, because when you put downward pressure on the blade, the pressure is going to engage the lock face. It's going to go off the pivot, and then what it's going to do is it's going to want to try to bend the lock bar in some direction. So if you're pushing down here, the blade is folding at an angle. It's going to be relative to the pivot, and it's going to go at 90 degrees to the lock face. Okay? So the closer the lock face is to the center line of the pivot, the more this arm, this little imaginary arm, is going to go down. And then it's going to spread the load, distribute the load along the length of the lock bar. That's going to help reduce the opportunity for the lock bar to have the geometry change as it tries to flex. And it's also going to direct the force straight back, which is going to make for a stronger lock. Also, coupled with that, if the lock bar flexes up, what's going to happen is that lock geometry is going to change because it's moving. So you're effectively just modifying, so to speak, the lock geometry if it's flexing. So you always want to try to get, so here's your pivot, front of your frame. If you're back here, supersize this so it's easier to see. You're going to hit your lock face, and it's going to come back at 90 degrees. That's bad. Okay? Here's your pivot again. If you have your lock face here, and say you do a little arc, and you come up, and then all of a sudden you have a nice wide lock bar that's not going to flex very much. Now, when the force is distributed down on the blade, your moment moves back. This is good. Okay? So, lock bar needs to be as close to and below center line of the pivot as possible. You have to take everything into consideration. That's going to be stop pin location, detent location, all of it's relative. You just have to make do with what you have. Now, am I saying that this cannot work? No. I've seen it work. It's black magic. Don't trust it. This works. I've seen this work. Many people do it. Many knife makers have accomplished many awesome feats doing this. I've only seen a handful of makers do this and not have problems with the lock, so they say. Try not to do this. If you have no other option because you made this super duper fancy knife that everybody and their mother's brother's cousin wants to buy, and you can make this work, make it work, because ultimately, if you're making knives for a profit as your full-time job, you want to make money. But You need to make sure that your consumers are safe and they're not getting a bunch of lock stick, they're not getting a bunch of lock slip, and they're not breaking knives and cutting off their little squishy fingers that are covered in Doritos. So, you have to make sure that as a knife maker, you're not messing somebody up. Get it straight. Lock stick, lock slip, unacceptable. Have I never had that? Of course not. Don't be silly. I have dealt with many problems with knives. Probably more problems than most people will ever experience until they've made, 5 or 10,000 knives. That's because I've made 5 or 10,000 knives. So I'm trying to help you understand that all of this can work. From what I found in my experience, this is the best way to do it. As far forward and below the center line as possible. Okay, so we've covered that. It's just, this is the law of folding knives, okay? It works. I'll give credit where credit is due. I've had some conversations in the past with Bob Trezula. I know Michael Walker in passing. He invented the liner lock or the leaf lock, whatever you want to call it. These guys, I've put lots of time and energy into it. I've talked to, Mick Strider and just tons of other knife makers. And most everybody agrees as far below and forward of the pivot center line as possible. Now, if you can somehow manage to get your lock face ahead of the pivot center line, then you're going to start running into the exact same problem, but instead of bending the lock bar up into the frame, you're going to start bending it down. That's no good either, because then you're going to develop lock rock, which is the blade being able to rock even though it's locked, but then also you're much more apt to break this lock bar off if you bend it down than up. If you bend it up, it's just going to rub against the frame, so that's a little bit of a safety point. You don't want to go all the way forward of the pivot center line, even though it's incredibly difficult to even design a knife to do that, and it would probably look hideous. So I would err towards slightly behind the pivot center line, which is 99% of the time that's what you're going to get anyway, unless you're Ramon Chavez, and then you've got, lock bar that's awesomely, perfectly centered below the pivot center line, so kudos to you, Chavez. At any rate, let's wipe this off and move on to the next rant. Okay, so we covered LOL. Okay, so moving on. I'm going to check the video and remember what AOLF stands for. Okay, a few sips of coffee because it is awfully early in the morning, and AOLF stands for Angle of Lock Face. Memory. Who needs it? I've got 3 kids. I don't sleep much. So, angle of lock face. So, when I say angle of lock face, what I'm meaning is if you take your pocket knife, and let's see if I even have one laying around here, and I surprisingly don't. And I'm actually carrying a fixed blade in my pocket right now. So let me pause and grab a folding knife. Okay, so now that I actually have my ducks in a row here, and I grab some props, I hope this will help kind of give a better example than my crude drawings on the board. I am actually better at drawing than this, but you get what you pay for, people. Okay, so angle of lock face. What I'm trying to explain here, and I'll get the camera to focus in. This angle right here. This is the angle of the lock face. This just happens to be set up, if I'm not mistaken, the angle of this lock face is like 7-something degrees. That's not an arbitrary number. And let me explain that. And maybe, if I can get this to focus, you'll see it's a small angle. It's really not much. So, on this war spear, it's different. You can see the lock face in there, right there. Voila, there's your lock angle. Okay, so there are two lock angles that you're going to be dealing with. So, two angles. Glad I didn't spell angels. Maybe I did. Okay, so two angles. First is angle 1, and then angle 2. Okay, I know that probably doesn't make a whole lot of sense because that's a horrible drawing. I'm gonna work on that. Okay, angle 1. The first thing we're gonna deal with is angle 1. Angle 1 is the angle of the lock face perpendicular, that's at 90 degrees, to the flat. Okay, that angle, I shouldn't say 90 degrees, it's not. That angle is really relative to the knife. And it also couples in with the length of lock bar, LOL. So the length of your lock bar, if it's yay long, you know, 2.5 inches, whatever, the angle of the engagement surface is going to change. Now, what you have to take into consideration for angle 1 is, you know, you get a lot of people that will just tell you, oh, cut your lock at 7 degrees, cut your lock at 8 degrees, cut your lock at 9 degrees. It doesn't work. You know, the angle, that angle is such an arbitrary number that nobody can tell you what's going to work for your knife. The only thing that's going to work for your knife is some science, and the fact that you have to trial and error it until you get it correct. So here, let me move angle 2 out of the way here. Let's move angle 2 so I don't forget what angle 2 is. 2 is the angle right here. And of course you hear the dogs in the background barking at the employees coming in, so pardon the interruptions. Okay, so the first angle is relative to the blade flat. So as you have your blade here, and then you have your frame, I'm going to leave some space just so that you can kind of see what's going on here. As the blade engages the lock, let me pause this. Okay, so back to it. Pardon the distraction there. I'm going to start a little bit more from scratch here because it's kind of difficult to explain this on a whiteboard. So, lock geometry, this angle is going to be, so this is your blade, and then this angle is the angle everybody gives you an arbitrary number on. So as your lock bar moves in, what's going to happen, and here's your lock relief so that it will bend and it'll actually be flat. Okay, so as your lock bar comes to engage, you have to have an angle here. Otherwise, the lock bar would just kind of travel past it. Or, if it was nice and flat, it would just slap into it and wouldn't do anything. So, you need to have some kind of angle here so that you have some built-in wear to the lock, but also something that's not just going to be a ramp and let the lock bar slide off. I use a curve lock face, just a shallow curve. People have gotten away with a flat lock face. I don't particularly agree with a flat lock face, but you know, it is what it is. Some people can get it to work, more power to you. I have a feeling that they deal with a lot more lock sticking and slipping than I do. But, you know, I don't really, I tried a flat lock face 2 or 3 times when I first started this, and I just really didn't like it. So, I don't do it. But I'm sure you can make it work at some point or another, because many people have. So what happens here is you have this angle. You can't just do an arbitrary angle like 7 degrees, because the length of this lever relative to its moment point is generally in the middle of your lock relief. This distance is your length of lock bar. Okay, so that also will give you the radius of lock face. That's the simplest way I've found to create the proper radius for your lock face on the blade, is to find your theoretical moment point of your length of lock bar, and then use that as the radius from, as I'm hoping most of you have passed 9th grade geometry, that your radius is from the center line of a circle to the outside edge. That's your radius. That's the length of your lock bar as well. So if it's 4 inches all the way around, you have a 2-inch radius. Then it works great, because there's a lot of people who will tell you just use a 2-inch contact wheel on your grinder and grind your lock faces. I don't think anybody's actually realized that, like, you can fudge this a little bit so a 2-inch wheel works perfectly. I think people are just tried it and like, oh, it works, cool. Okay, so understanding the science behind things is really cool. Science is awesome, kids. Stay in school. Or if you homeschool, stay at home and have your parents teach you this. Hopefully they know geometry. So we have a 2-inch length of lock bar. We have a 2-inch radius. Let's just keep this math simple. Most of my lock bars end up being a little bit longer than that, so my radius a lot of times is like, you know, 2.3654321. You know, it's crazy. And when you're using a you know, SolidWorks or AutoCAD or Fusion 360 or whatever you're using, you can have crazy tolerances that you can never meet in real life. So you do have some fudge factor when it comes to the radius and your angle there. So that's how you find the radius of your lock face. The radius, now let me expand upon this a little bit. If you have perfect tolerances, you know, plus or minus 0, okay, not attainable, but whatever. For the sake of argument, say you have that. You have a lock bar that's 2 inches long, you have a radius that's 2 inches, and you have perfect setup. What's going to happen? That lock bar is going to come over here, and it's still going to just pass by and never really touch. I mean, realistically, it may actually touch in the back corner, but realistically, if you have a 2-inch radius here with no angle to it, it's never going to touch. It's just going to pass on by it. So you have to create an angle so that you have interference. If you don't have interference, you don't have a lock. Basically, it's just going to rattle around like a maraca. We don't want that. Everybody's experienced the custom knife where they're like, look, I've got a really expensive maraca. Don't do that, kids. Okay, so what you want to do is you want to add an angle, an additional angle to this radius. So how do you choose the angle? You don't want to just say 7 degrees, 8 degrees, 9 degrees. What you want to do is what works for your knife. There's a couple of things that you have to take into consideration when it comes to that angle. So let me erase this and we'll go into that. Okay, so once you have the radius figured out, the angle of the said radius. So again, here's your blade, looking kind of from the choil, the plunge into it. So say you have a slight radius there and a little bit of an angle. You have your lock bar out here, radius. Okay. Now this angle here is going to need, it can be anywhere from, I would say, 6 degrees to 8 degrees is going to be your plus or minus, so to speak. Be within, 6 to 8 degrees. That's a pretty big span. So how do you choose that? Again, trial and error. The flex of the materials like titanium and the width of the lock bar, creating some flexion, whatever the term is, flexion, deflection, flexion, whatever, is going to determine some of that angle, because the lock bar is going to flex a little bit and you're going to get some movement. So you want to choose an angle that works properly. Okay, so in my perfect world, I would have the least angle as possible, only because that's going to give you the strongest lock possible. At the end of the day, you have a lever that's on a pivot pushing against an angle. Okay, so you've just created a ramp. So at the end of the day, the shallower that ramp is, the less likely that it is going to be able to slip off. Now, collectors, God love you because you pay the bills, but you guys are a finicky group of people, and you don't like it when you can take a knife and push the lock bar over. Only, and I say this lovingly, only through sheer ignorance do you not like that. You think that, oh, I squeezed the knife and it locked up tighter. I don't like that. It's going to wear out. Okay? You're wrong. I'm sorry. You're wrong. It's not going to wear out faster if you've chosen the proper materials and the proper geometry to do that. But you guys hate it, so I don't do it. Because at the end of the day, you guys are the ones that are buying these knives. So I have to do what you want me to do, even if it's not right. Maybe through education I can change some opinions, but I'm not counting on it. I'm just going to do what you guys want. Whatever. But realistically, if you went 6 degrees and you had proper interference, you would be able to take your lock bar, push on it, and it would flex the material out of the way, and that lock bar would travel all the way across the backside of the blade. You would be able to unlock it very easily, close it, flick it back open, and it would go back to the original position in which it was designed to go. It's not going to wear out, it's not going to permanently bend it, it's not going to destroy it. But you guys don't like the fact that you can squeeze the knife and all of a sudden the lock bar traveled all the way over to 80 or 90%. Whatever, is what it is. So we ended up increasing the angle until it was more difficult, not saying impossible, but more difficult to push the lock bar over. So let me zoom in here and show you. So what's going on here is when you open the knife, we like our lockup to be about 30 to 40%. That's safe. But what ends up happening is if you push on it really hard, oh, look at that, it just moved. Because the lock bar flexed away from the frame a little bit and collapsed some of this material slightly and pushed over. But look at that, it still locks up exactly where it's supposed to go. Imagine that. That's proper lock design. So choose an angle that people are going to be happy with, knife makers, but choose an angle that's going to remain safe. The steeper you go on the angle, the more problems you're going to have with lock slip. So you want to choose the proper radius, the proper lock bar length, and the proper angle. Trial and error. Most of our locks are like in the 7-degree range, depending on the lock bar length and the knife itself and the width of the lock bar. By width of lock bar, I mean width if you're looking at the flat of the frame, the width from the cut to the bottom. This width is going to determine how much that lock bar can flex up and down. So, you know, you have to take all that into consideration when you do this. So again, lots of trial and error. But to get that angle anywhere from 6 to 8 degrees, do some trial and error, figure out what works for the knife that you've designed. And then what I like to do is just cut the angle shallow, test it, cut it a little steeper, or excuse me, cut it steep, like 8 degrees, test it, cut it a little shallower, test it, cut it a little shallower, and cut it until it gets to the point where you can easily slide the lock bar all the way across and then back up. On the next knife you do, go a little bit steeper. And then split the difference. Find the point at which it'll slip, find the point at which it will not slip, and then back up just a little bit so that you can't just push the lock bar over, and it's perfect. The way I've designed it, I optimize all my lock geometry to where this is through many years of experience, when I'm setting lock faces, I will actually whack the back of the knife and the lock bar will actually engage further instead of slipping off. That's only through trial and error that I have been able to manage that. Don't try that at home, kids. You're gonna cut your finger off or put an eye out. I don't recommend spine whacking. It's the most retarded thing ever freaking developed on the face of the earth. You don't use the backside of a knife. If you errantly hit the back of your knife on something while you're cutting something, 1, stop doing that. But 2, the lock should not close. It should be safer than that. And also, what are you doing when you're using a knife? You're squeezing the lock bar. Well, the lock should not engage because you're squeezing the lever against the lock bar further. So again, don't spine whack things. It should be able to withstand pressure on disengaging the knife because it needs to be safe. But at the end of the day, spine whacking is not a good test. You know, it's already a broken fixed blade being a folding knife. Just leave it as that. If you need a fixed blade, go buy a fixed blade or a crowbar. Okay, so moving on to curve or not to curve. Okay, so now we're going to move on to the next angle that you have to deal with. This one deals with mainly combating lock rock. So looking at the flat of the knife now. Again, crude drawings, forgive them. So what you're going to run into is you have your lock bar comes down. You've got all your angle 1s. This is angle 2 that you're dealing with. And this is the engagement point. So what's going to happen here is if you have this big old long lock bar, you know, say it's a 1/4 inch wide, you know, 250 thou, okay? You can't just engage your lock face on the entire width of this lock. It doesn't work. You're gonna have too much engagement, you're gonna get lock rock. So what you wanna do is you wanna engage this bottommost portion here of the lock face, because then you're gonna have a slight gap back here. And what's going to happen there is it will account for some wear, and it will also prevent the lock from having a flat surface to rock against. That's why you get lock rock. Typically lock rock is because it engaged the back side of the lock bar, and then when you flex it back and forth, it's creating a gap at the tip of the lock face, and then it's rocking back to the engagement point. You have a lot of pressure. If you put pressure at the tip of a blade, say it's a 3-inch blade, and it comes back, you know, almost 4 inches to the pivot, that's a long lever to put pressure against the small little area. So it's going to create a lot of deflection in the materials. Titanium is not a very strong material. I don't care what anybody tells you how cool titanium is. Titanium is really not that great. But at any rate, that's a rant for another day. So you have to give an engagement point of the lock face that's all the way down at the tip, and I say this as the tip of lock bar. That's the tip. Now, you don't want to just engage a little, 10 thousandths width piece. I've found, optimally, that anywhere from 80 thousandths to 100 thousandths of engagement is optimal for that surface. So, let's erase this a little bit so that I can do some more drawings. So, when this lock face comes down, I want that surface to be slightly proud of the rest of it. And I'm only engaging this surface. Okay, 80 to 100,000. Anything less than that, you're just reducing strength. But anything more than that, you're going to run into issues with lock stick. Just generally, you're going to run into a lot of problems. So typically, you want 80 to 100 thousandths of lock engagement at the tip, and you want this to bias to the tip. Okay. So optimally, you'll have a clearance angle in here of, say, a 1/2 degree. I'm getting really complicated here. That's because I have some very nice CNC machining centers that I'm able to do this sort of thing. So some of this is going to be by eyeball and a magnifying glass for you guys that are just doing this on a Bridgeport or a grinder. So deal with it. That's life. That's why it's really hard to be a custom knife maker. Yes, I am still a custom knife maker, but I also manufacture knives. So I have the benefit of hindsight and, a little bit more capability. You'll get there. You just have to keep putting one foot in front of the other. So you want a slight bias towards the tip so that you do not get lock rock, but it's also going to give you a little bit of wear in, and then it will account for your plus or minus tolerance when you're either A, machining, or B, grinding or fitting with a freaking Dremel tool and a file. It's going to give you a little bit more leeway in there. So you want a little bit biased towards the tip, but 80 to 100 thousandths lock engagement surface is optimal. That's the strongest you can get, because realistically 80 thousandths is much thicker than my 60 thousandths thick titanium lock relief that I have back here. So you always want to have everything as strong as the weakest, stronger than your weakest point, and know where your weakest point is, because that's your mode of failure. So that's that lock engagement. That's also your angle, number 2. You have a slight angle down there, but you still want to maintain an 80 to 100 thousandths lock engagement surface. That angle 2 that I'm talking about here, that couple thousandths worth of angle right down there, that's going to go away as the knife wears in, and you're going to have 80 to 100 thousandths. You only put that angle in there to prevent initial lock rock as it wears in. Then as the lock bar wears in, it will travel over slightly. It'll wear that surface down to where you'll probably have, you'll probably end up at the 70 to 80 thousandths lock engagement if you shoot for 80 thousandths and you put a a 1/2 degree or a 0.2 degree angle to it, so it's a slight more pressure towards the tip in the rear. It will wear in, and everything is plus or minus tolerance. You have tolerance, stack, all these parts have to fit together. So you want to give wear points to where you know they're going to wear, not to where you're guessing. So you give a little bit of an angle there, and that allows for wear in, and then you have a perfect knife after you've opened it 3 or 4 times. Or in the way we do it is we give that tiny little bit of an angle, and as we're assembling the knife, you whack the back of it while you're pushing on the lock bar. You spine whack it on the counter as you're assembling it, and you're holding the lock bar in place, so that what happens is it slightly peens that surface, and then they mate perfectly. That's why it's so difficult to just say, I want to replace the lock insert on my knife. Well, everything is fitted and worn in together. So, you know, it comes back to the factory if it ever ends up happening, which so rarely happens unless somebody loses one or something, or they decide to modify it for some silly reason. But those surfaces are for that knife, no other knife. It's very rare that you can, after you've fitted several knives together and you've got them all working and you've used them a little bit, that you can interchange those parts any further. Our goal in manufacturing is to have part number 1 fit part number 1000. We're able to do that, but after you assemble the knife and you've used it for a while, those parts have worn together so finely because of the tolerances that we've set up that you can't just take that part and put it on another used knife because it won't work the right way. You know, sometimes you can get away with it, but, you know, even a blind squirrel finds a nut every once in a while. Okay, so that kind of covers all of that setup. You know, we'll do a couple more videos on, like, detent, optimal detent location and stop pin track. You know, just, you know, a little prelude to that. I am moving more towards external stop pins than internal stop pins. Yes, it's much more difficult to design with an external stop pin because you have, you know, this big old pin that's in the way, but it does allow for a more maintenance-friendly knife compared to an internal stop pin knife. But I won't get into all that, just a little prelude to some of that information. So if you have questions, you know, ask in the comments, shoot us an email. I'll do my best to respond. Like I said, I'm super busy, guys, so that's why I'm doing the video, so I don't have to, like, respond to a bajillion emails and comments, but I really try. I want to engage with you guys more and more. I'm trying to pull my head out of the machine shop realm to, you know, get back into spreading the knowledge, hence the reason we have the Professor Hoback series. So hopefully you guys really enjoyed the video. Please follow us on Instagram, follow us on Facebook. We're really trying to fix the Facebook. We've got lots of issues with Facebook. You know, check out all of our social media. Go to the website, jkobackknives.com. We'll see you at Blade Show 2020 here in a couple of months. Really excited to see y'all. So if you have questions for me, you know, shoot me a message, you know, comment in the YouTube or Instagram or whatever. And we appreciate you guys. Thank you.